So our focus is primarily going to be on something called classical multidimensional scaling, classical MDS. The reason it's called classical MDS is that we're only interested in Euclidean distances. So that's the sum of squares distances, or as a crow flies distance. So suppose someone comes along with a data matrix D, which is an n by n distance matrix, or dissimilarity matrix. Then we say that D is a Euclidean distance matrix if there exists a set of points x1 to xn that are in Rp for some dimension p, such that the interpoint distances between them is given by the distance matrix. So in other words, if the Euclidean distance between I and j is dij. Okay, so remember Euclidean distance is xi minus xj transpose times xi minus xj all square rooted. So we may not know these set of x points. So what we're going to do now is going to write down a theorem that tells us how we can know whether a distance matrix D is Euclidean or not, and how, if it is Euclidean, to find a set of points x that meet this requirement. So how to find a set of points that has the right interpoint distances. So classical MDS doesn't work directly with the distance matrix. It instead works with something called the centered inner product matrix, which has various names in statistics and machine learning. It's sometimes called a gram matrix, or it's sometimes called a kernel matrix. But these names aren't going to make sense to us yet. They will do once we see the theorem. So the centered inner product matrix corresponding to a distance matrix D is, and we're going to call it B here, it's minus a half times H, then we've got the Hadamard product of D with itself times H, where H here is the n by n centric matrix. This Hadamard product, or element-wise product. And so if A, let's say A is D, Hadamard product with D, then the element Aij is just the element Dij squared. Yeah, we just multiply the elements, the matrices element at a time. So what we do in classical MDS is we're going to try and find a set of points that has a centered inner product matrix B approximately equal to the one corresponding to the data, the distance matrix D. Okay, so we're now going to state the main result that we're going to rely upon for classical MDS. So the first part is kind of the less interesting part, but it says that suppose we've got a distance matrix D, and that we've got its corresponding centered inner product matrix B, which as we've just said is minus a half H, the Hadamard product of D with itself H. Okay. Then the theorem says that if D is a Euclidean distance matrix for some set of points x1 to xn, then one way to compute B is to do the centered version of x times centered version of x transposed. Yeah, so how do we center x? Well, we do hx. Yeah, so remember, hx has the effect of subtracting the column mean from each row. So we'd get the matrix that is x1 minus x bar transposed down to xn transposed minus x bar transposed. Okay, so yeah, these are row matrices, row vectors. Okay, so we're going to see that element Bij here is just going to be xi minus x bar transposed times xj minus x bar. Okay, so if we have the data coordinates, the feature vectors x1 to xn, then an easy way to compute the centered inner product matrix B is like this. And we can also see straight away here that, let's add that B must be positive definite. Yeah, if you think about what positive definite means, it means that A transpose B A is bigger than or equal to 0 for all choices of the vector A, while this would be A H X transposed times, and if we work this out, it will be A transposed H X. So this must obviously be bigger than 0. Okay. So if D is Euclidean, B is positive definite. Oh, sorry, I should have a typo here. Positive semi-definite. D Euclidean implies B is positive semi-definite. Okay, so the second part of the theorem is a converse to this first part. So the first part said, let's suppose that D is Euclidean for data points x1 to xn, and then said something about B. It said that B is positive definite and can be computed this way. The second part, we're going to start differently. We're going to start with B. Okay, so it says, suppose B is positive semi-definite. Let's suppose it's got with rank R, so with rank K, and then it has spectral decomposition B, which is U lambda U transposed, where U is going to have to be N by K, with U transposed U equal to the identity, and capital lambda here is going to be a diagonal matrix with the K positive eigenvalues. Okay, so lambda 1 bigger than or equal to lambda 2 dot 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 bigger than or equal to lambda K, which is bigger than 0. Okay, so suppose B is positive definite, and now we're going to say something about X and D. So the theorem says, if B is positive definite, then it tells us how to form an X. Okay. Then X, which is made up of rows x1 down to xn. Okay. X, which is U square root of lambda. Then X is an n times k data matrix with Euclidean distance D. Yep. So we started by saying assume that B is just a positive semi-definite matrix with rank k. Then we've defined X to be U times lambda, where U and lambda come from the spectral decomposition of B. And if we define X in that way, then the theorem says this is a data matrix that has Euclidean distances D. Yeah, so if we work out Dij is the Euclidean distance between xi and xj. These points x will have the right distances here.